Okay, this is second video in probability functions, really a bit more on density and mass functions, probability functions. We introduced this in the last video, but this really is just a little bit more detail on that, and just showing how they work and the sort of questions that might come up in examinations. Okay, so let's have a look at this first one then. The discrete random variable x has probability function. Okay, so this is how we've described it. The probability that the random variable takes value x depends on x. And it's this little formula here for x is 0, 1, and 2. So for instance, if x is equal to 0, then we've got k times 2 minus 0, 2k in other words. So that's what we've got here. And then for 1, it's 2 minus 1, 1k, there we go. And then 0 plus 2 minus 2, 0. And then finally, we've got this other value, k, for x equals 3. So k into 3 minus 2, that's k. And otherwise, 0. So it goes on to say, k is a positive constant, show that k is equal to 0.25. Well, if we add these up, we know that all the probabilities for a discrete probability function have to add up to 1. So this adds up to 4k. So 4k must equal 1. Therefore, k equals 0.25. So that's that first bit done. Two independent observations of x1 and x2 are made of x, show that the sum of them equals 5 is equal to 0. Right, the only way that possibilities that give us a total of 5, or if we do a 2 and then a 3 for x1 and x2, or if we do a 3 and then a 2. Now, because these are independent observations, then the probability of this is equal to the probability of the product here. That's going back to our probability section. And the probability of this is 0, because obviously the probability of 2 is 0. This is a 3 here. Probability of 3 times probability of 2 similarly equals 0. So the probability of both of these combinations is 0. In other words, we're never going to get a 2, are we? So that is why that is 0. And then it says find the complete probability function for x1 plus x2. Okay, so yeah, again we've got 2 observations. So the minimum we could get is 0. The maximum is 6, isn't it, if we get 2 3s? So here's our table that goes from 0 up to 6, and I've kind of given the combinations here. I've abbreviated it, so getting a 0 and then another 0, I've just written 0 0 and so on all the way through there. Probability of 0 0 is basically well, it's 0.5 times 0.5, again independent observations. So that's 0.25. 0 and a 1 is at 0.25, 0 and then a 1. So that would be 0.5 times 0.25. That's that 0.125. And then a 1 and a 0 is the same, is 0.25 times 0.5. That would be that. The sum of those, these are mutually exclusive events, so we add those probabilities to give us 0.25, and then we just work our way through the others. Basically, I've not kind of detailed it. I've just given the outcome here. Obviously, anything with a 2 in is going to be 0, so that's going to be fairly simple. So a 1 1 is going to be 0.25 times 0.25, and so on. So completed all those, and by way of a check, if you add all these horizontally, it gives you a total of 1, which gives us confidence that we've done the right thing. So that would be the complete probability function for x1 and x2, and we quite entitled to write it, draw it like this. And then finally, find the probability that the sum of these two which in a sense is a new random variable, isn't it? We've created from these other two, is greater than or equal to 1.3 and less than or equal to 3.2. Well, obviously it can't be, it can't be a decimal value. So it's got to be greater than or equal to 2. Okay, so that's the next, because that's the next integer value up, and it's got to be less than or equal to 3. So anyway, it's got to be 2 or 3. And that means we just have to add these two things up here, and that gives us an answer of 0.3125. So that is the probability. That's the answer for C. Okay, so that's a fairly typical kind of question that you might get. Let's have a look at another one. Well, there's two here on this page. This is a simple one. I used this table before. Discrete random variable has the probability function shown in the table. Okay, we'll just listed out those 4 values. That is a way of describing a probability function for a discrete probability. And just one simple question: find a probability that x is greater than 1 and less than or equal to 3. Well, that must be these two together. So these are mutually exclusive again. So we add these two together. 1/12, 1/12, that is 1/6. So that is the answer to that one. The random variable x has probability function. Probability that the random variable is equal to the value x is equal to k times x. Show that k equals 1/15. Okay, so if we write this out, all the different values of x that we can have, 1 to 5, then the probabilities, we're just applying 1, 2, 3, and so on to that. We're going to be k, 2k, 3k, 4k, 5k, which add up to 15k. 15k equals 1, because obviously they all add up to the sum of all these adds to 1. So 15k equals 1, so k equals 1/15. And then the probability that x is less than 4 is going to be these 3. It can be 1, 2, or 3. Mutually exclusive again. K plus 2k plus 3k is going to be equal to 6k, and that is 6k. Basically, since k is 1/15, that's a total of 6/15, or 2/5 expressed in the simplest form of a fraction. Right, okay, so those are all to do with discrete. Let's have a look at this one. A continuous random variable x is uniformly distributed over the interval -4 to 6. Write down the mean of x. Incidentally, I might just say at this point that a uniform distribution like this could actually be, well, it's discrete or continuous, could be quite useful in the sense that if we don't have any other information to go from, when we're looking at probabilities, we often just need a basis for making our decisions. And therefore, we may well use a continuous, a uniform distribution. For instance, we were betting on the outcome of the Saudi Arabian football championships, and we were given a list of a dozen teams, and we're to bet on them. If we don't know anything about Saudi football, we might just need to assume that each of them has an equal chance of winning. Probably not true, but if we're trying to make some decision, when we're placing a bet or something like that, then that might be what we want to do. Is it going to rain tomorrow? It can either rain or not rain. 50-50 chance. We might use that. So uniform distributions kind of tend to be used like that, because at the end of the day, what we want is a basis for making decisions. So that said, let's go back to this question. Oh, right. This is between -4 to 6. Write down the mean of x. Now, well, I won't really cover this at the moment, but I think I mentioned before that if we're going to find out things like the expectation of X, in general, when we're dealing with continuous probability functions, we really into the business of doing of using calculus. This is a definite integral here, which you may recognize if you've covered that that discipline. So yeah, so what we're doing is just integrating the value times the probability over this interval. Now, I'm going to do an example like this in a moment, but this is a uniform distribution. The expectation of the random variable is basically what's right in the middle, and obviously that is 1. So 1 is the mean. So about the mean, I mean, normally talk about the expectation of X. It's pretty well the same thing, really, but the normal thing when we're talking about random variables is to talk about the expectation. So so that's that. Second part, find the probability that X is less than or equal to 2.4. 2.4 is about here. So it's really, you know, this is these are the values that the random variable could take, and therefore the probability is this area sort of above it up to the line. And that's what that's going to be. Well, it's a rectangle, isn't it? Base, and the length of the base is 2.4 minus 4. What's that length? And the height is 1/10. Multiply that out. That's going to give us 0.64. So that is the probability. And also find the probability that -3 is less than X minus 5 is less than 3. Well, this is just a bit of a kind of a tricky way of stating the probability that X is actually greater than 2 and less than 8. So all we have to do is just solve that inequality in both directions. Now, it can't be between 6 and 8 because it's uniformly distributed over that interval up to 6. So it's really, we're looking at the probability that the random variable is between 2 and 6. And that's 6 minus 2 times 1/10. Put my brackets there, but that's equal to 0.4. So that is that's how we would do that. Okay, so that is a continuous uniform. I've got another one with continuous uniform. I mean, it does come up quite a lot in this sort of question, really. Let's have a look. The continuous random variable y is uniformly distributed over the interval a to 4a, and we don't know what a is at this point. So the first part says use integration to show that expectation of y squared equals 7a squared. Now, if you haven't done calculus, then you know, don't worry too much about it. But for those that that have, then you know, just follow this through. Otherwise, you should just be able to sort of glean the general idea from it. So what we're saying, and I think I mentioned this before, is that when we have a continuous, rather than a continuous random variable, instead of summing up all the things like we did with the dice, multiplying the value by the probability, what we're doing is we're actually doing the calculus process, and we're multiplying the value y by the probability, the value of the probability function at that value of y, and it's the same all the way along. So, so it makes things a bit simpler, and we're doing that with respect to y. So that's what we're doing, and of course we're doing it between a and 4a. So right, so if we just work that one through, then this p of y, this is basically this value here, is 1/3a. And just to go over that, of course, this length here is 3a. So in order to make this area 1, then the height must be 1/3a, because 1/3a times 3a equals 1. So that's how that works. So this 1 over 3a is that. Here's your y. There's your dy. We've got our limits there. We integrate this. We get y squared over 2. This is a constant, so that is unchanged. So we're evaluating between 4a and a. And that's that 2 goes with that 3a to give us 1 over 6a. And then we basically sub our 4a into that y, plus 4a squared, and then subtract off a squared here. So that's going to give us all this lot. 15a squared over 6a equals 5a over 2, which we note is actually the middle. So we could have saved ourselves a lot of trouble just by noting that. But I just thought it was kind of worth going through that process. So if you're more complicated function, some probability function, which does actually depend on the value here, isn't just a constant like this, then you'd apply that principle. And then he goes on to say, use integration to show that the expectation of y squared is equal to 7a squared. Now, remember from before is we need this in order to calculate the variance. So expectation of y squared, well, we're doing more or less the same thing, except our y, then we are actually using y squared. So this is constant in this case because it's uniform, so that's that. Once we've integrated this using the power rule, we add 1 to the index and then divide by the new index, and that's y cubed over 3, and we evaluate between 4a and a. This 3 goes with that 3a, so that's 1 over 9a, and then we've got this evaluated at 4a, which is going to give us 64a cubed, minus this evaluated at a, which is just your a cubed, and that's 63a cubed divided by 9a, so it's going to give us 7a squared. Okay, and the variance is the expectation of y squared minus the expectation of y squared. E squared y, we'll write it like that. And that's so we just make the appropriate substitutions from here and here, and it gives us 3/4 a squared. So that is that's all we'll do here. So yeah, so if you've done calculus, then follow that through, and you know that's the same principle you may wish to apply. You may need to apply elsewhere. If not, then just kind of hold that thought until you've done some calculus, and then you'll be able to perhaps come back to this and see how it works. Okay, so that's basically it. So hopefully that has been useful, and I'll see you in the next video.